So hello everyone, my name is Antonia. I'm one of the founders of Chatshopper, a fashion chatbot startup in Berlin. And this is my colleague Chris, who's a data scientist, and he will later talk a bit more about the product details. I will tell you more about the learnings and what we do and why we do it. So we built a conversational commerce layer for fashion online shops to actually enable their users to search products on conversational interfaces such as chatbots or voice assistants. We believe that the internet is no longer only a browser, and there are actually now more users in messaging apps than on social networks. So also the big players, all of them, they are opened their APIs for third parties, and with those new devices such as Amazon Echo, new entrances to the internet actually emerge. Conversational commerce, that's the term people talk about when they talk about bots or voice. It leads to 24 and instant available communication. This means your users will get much more impatient because they will expect the automated system to answer their requests and not wait for a customer service person for 5 or 10 minutes. What we see is that this leads to a change in user behavior, to natural language search, especially like before you typed in a keyword like blue and jeans, and now people start talking like, I'm looking for a blue jeans for this summer. And we also see that there are much more complex searches. For example, people no longer just search for a jacket, but they are looking for a jacket with some feather on the neck or something like that. Like really weird things which you normally don't have in traditional search fields. So why I'm standing here, why I'm telling you this, in 2015, during working for Otto, I had the idea for a shopping service via chat. Back then it was on WhatsApp only, and we had like humans answering the requests. The users really loved it, and within 2 months we had so many requests. We were kind of always answering requests ourselves and employing more students every week to actually handle those requests. But we also learned really fast that humans scale quite bad, and we shouldn't scale with humans because they are expensive, they are slow, and you never know how many requests will come in, so better try to solve it in a technical way. So we built our first chatbot in the end of 2015, which overtook operations in 2016 from the human agents. So 2016, we focused mainly on natural language understanding because we wanted to automate the requests. We tried a lot. We tried a lot of off-the-shelf solutions like with AI, but we ended up building our own solution because we realized on the one hand side, the available solutions weren't, it wasn't possible to actually adapt them to our really narrow use case, which was like a conversational fashion search, but also they also had some issues, and for example, with AI regularly had API response times from over 1 minute, which when our chatbot just crashed. So on the one hand side, when you understand what your users are looking for, so if you are good in natural language understanding, you still have the challenge that you actually need to deliver what they are looking for. So that's why in 2017 we focused mainly on the data quality and data quantity, because even though we understood quite a few things, like a lot of people back then were looking for destroyed jeans, but the data didn't say or the filters weren't available for destroyed. So we worked on the one hand side on our own conversational backend, which is also able to handle status, but also user data and previous sessions, but also the data enrichment. So we look at product images and try to extract data out of it. So is there a model in the picture, or is it a close-up image, or is it a pure product image? Then we look at what information do we see, like a category, color, style, and all those things. So we don't rely on the existing data, but we create data with the help of neural networks. So that's a bit the solution overview, but today we want to talk about the fashion or the natural language understanding part. Here you see a typical request, in this case from Amazon Echo. So someone is looking for a suit in black for under 200 euro. So the NLU gives us back the relevant intent. Intent means what is this person, what does he or she want? So in this case it's a request, but it could also be a hello, how are you? Or what's your name? Or how does shipping work, or whatever comes up. We handle quite a few intents at the moment, but also you need, if it's actually like a request, you need to identify the correct entities to actually do the search. So in this case, we need to know what's the category, the color, and the price. And now Chris will tell you a bit about more how we actually come to these intents and entities.
Yes, hello. So as Antonia just mentioned, so up here we have the intent classifications from our natural language understanding engine. And down here we have all the entities that the engine found for this request. Yeah, I need a suit in black for under $200. So I'm going to talk first about basically how we do this intent classification, and then afterwards I'm going to talk about how we do this entity classification. Oops. Okay, I need to. This is somehow shifted. Okay. So, can I maybe ask up front? Do you guys know about machine learning and what sort of the idea is behind machine learning and how it generally works? Maybe a show of hands for everyone who knows about it. Okay, so most people. So then I'm not going to talk about sort of like the basic idea of machine learning. I'm just going to say what kind of machine learning models we deployed here. So the goal is to classify each user request into one of 41 intents. So we have intents like, for example, is it a feedback negative? Is it a feedback positive? Is it a greeting? Or is it a product request? Which of course is kind of the most important intent for us. So yeah, we wanna have a solid, reliable classification in order to sort of like let our bot handle each and every intent in a different way. So a product request, basically the bot would then show product recommendations, or if it's a feedback negative, the bot would then say, hey, tell us what went wrong, or please, yeah, I don't know, send us an email or something like that. So based on different intents, the bot will react in different ways. So the intent classification is majorly important for the whole bot experience. And we played around with two intent models. One is a support vector machine, and the other one is a recurrent neural network. So I'm going to talk about each of them and what we did there. So first of all, when it comes to, yeah, especially for the intent model, but basically always in machine learning, when you work with text, quite often you need to have some sort of numeric representation of a word. So it is, for example, if we would just sort of like take a dictionary of all the words we have and just assign a random ID, we would lose a lot of information because there's, for example, no semantic relationship between, for example, a dog and a cat. They just would have one ID, but they share a lot of attributes, that they're, for example, an animal and all this kind of things. So if we would have a numeric representation of words, it would help our machine learning model to make classifications. So one very popular approach to encode words into numeric vectors are word embeddings, which are sort of learned from a machine learning model itself. One really famous one is word2vec. I don't know if you guys heard about it. But basically the idea is the numeric representation is learned from the context of each word. So the nice thing is that we end up with vector representations of words that actually sort of like make sense in the sort of space they live in. So for example, if you have a three-dimensional space here, so every word would be sort of like a three-dimensional vector. And we have, for example, a vector king here. So this would be the king. And for example, we could then deduct the vector man, so we would end up somewhere here. And then we could add the vector woman, and we would end up at roughly queen. So you can see that you can even do sort of vector operations between these word embeddings that you learned, which is a really nice feature. And it basically, yeah, shows us that there's some sort of semantic information encoded into them that is very sensible for us humans. And this is another example that from sort of a present tense to a past tense, whether it's walking to walked or swimming to swam, those vectors are very similar. So they just basically, yeah, they just give a direction towards past tense in a way. So it's very popular and very successful to use word embeddings. I'm just gonna switch back to the previous slide. Then there's one problem for our intent model. Okay, so we have a sentence and we have a vector representation of each word, but we need like sort of a sentence representation now in a numeric format. And one really crude approach is to just sum up all the word embeddings to arrive at one sentence embedding. And don't do the math here, it's not correct, it's just random. So yeah, so then we just take basically the sum of each word embedding, which at first sounds like a really sort of crude and stupid idea, but it turns out that actually if these vectors are in a high enough dimensional space, you don't lose a lot of information. So a nice analogy for this might be, for example, assume, for example, you have like 1,000 students and each of them took a test with like 100 questions, for example. And you know the test results of each student. So, and now, for example, you have a sample of 10 students and you just know the sum of their test scores. Is it possible to identify each of the 10 students in your subsample of the 1,000 students? And you could think, well, if you just have the sum of all the test scores for these 10 students, it's going to be really difficult. But then you could think, okay, the more questions I have, the higher the probability that I actually will be able to identify which students were in this subsample of 10. And even better, if sort of like the test results are sparse, so that you have a lot of zeros, so students generally skip a lot of questions, then it's going to be even easier. So if you have like a high dimensional vector, and if it's pretty sparse, you can actually recover quite easily the students underneath it. And it's the same logic that applies here. Even though you take the sum, you can still recover with a high probability all the information of each individual word embedding, which yeah, you can also show formally. But that's why taking a sentence embedding as the sum of each word embedding works remarkably well, although it's sometimes a bit unintuitive. So we already had this slide here. So yeah, and then we basically we run a linear support vector machine on our, or we train a linear support vector machine on our training data. And as you know, in machine learning, you need sort of in your training data and supervised machine learning, you need like all the expression, the sentences, so the requests from the users, and you always need a label. So we need to know, like for all the training data, we need to have a label, which kind of intent this was. In our data set, we roughly had 10,000 expressions with labels. Yeah, then we just sort of fitted a linear support vector machine. And the whole idea in a support vector machine is, if you think now in two-dimensional space, so each word embedding has 2 entries, you could, and let's say you only have 2 intent classes. Then you would have one class here, those black dots, each is represented by 2 coordinates. And you would have the other intent class here, those white dots on the lower right. And then the support vector machine tries to find a hyperplane which separates these two clouds as good as possible. And good for a support vector machine is if the corridor is as wide as possible. So it's also called a maximum margin classifier. So it's a convex optimization problem, and yeah, it's a quadratic programming optimization problem, and it's very easy, or it's very fast to train, and it's fast to evaluate. And given that our word embeddings are in a high-dimensional space, here it's two-dimensional, but it's around 300 dimensions, and its sparse linear support vector machines work quite well because it can find a pretty good hyperplane that separates the data. And this is generally a support vector machine, and its plane mode is a binary classifier. So we have 41 intent classes. So you could take two approaches. You could either use like a multi-class SVM, which is a lot more complicated, or you can just run binary classification on all intent class combinations, and that's what we do. And that's usually the standard implementation in all those Python and other implementations of SVMs. So we ran many binary SVMs, and then we do like a majority vote to pick the class that is that has the highest confidence. Yeah, so the other intent model that we played around with was a recurrent neural network. And here, the thing is, you don't need the sentence embedding approach, which in a way works really well for SVMs, but sometimes it feels a bit strange to do that. In a recurrent neural network, you feed each word, and here it's, for example, I need sneakers. Again, each xt is a word embedding vector. You feed that at each time step, you feed it into the recurrent neural network. So there's no need to aggregate the whole sentence. It's word by word. So that's a nice feature already. And yeah, if you've seen recurrent neural networks before, it's basically you have a hidden state that gets updated at each time step. And this hidden state sort of captures in an abstract way what it sort of noticed in the sentence that is important for the classification. So while feeding in new words at each time step, the hidden state gets updated, and at the end of our request, we decode the hidden state to get an output. And this output then is a probability distribution over all our intent classes. So basically at the end here, the output will just give us like confidence scores on all intent classes. Yeah, so this is a plain recurrent neural network. They don't work well for long-term dependencies. So if we have long sentences, the hidden state does not tend to get trained well. So there's a cell type in recurrent neural networks called long short-term memory cells, LSTMs. This is what we use. And we also use them in a bidirectional way. So we go from front to back, and we also go from back to front. So yeah. So just to sort of like sum up and compare those two approaches, the SVM is faster to train and evaluate than a recurrent neural network. The RNN with LSTM cells and bidirectional has higher accuracy at 95% versus 93% for the SVM. So they're both really good, but the RNN is marginally better. And in general, although this is not really that important for our use case, as we can see from the accuracy, that is, I mean, they're almost the same. But in general, an RNN can model the order of words which an SVM with this embedding summing approach cannot. So an RNN theoretically could find out about the difference of only she called versus she only called, which yeah, is a totally different meaning. So given that we feed in each word embedding at each time step, we can kind of like model the temporal structure of a sentence with an RNN. Yeah, so that was the intent model. Yeah, so for the named entity recognition part, I'm just going to switch back really quickly to this slide here. Just so that you remember, so now we are talking about the entities here. And what is an entity? So, for example, in this sentence, we are looking, for example, the category, we want to pick up suit. So suit would be a category, and we want to pick this up in order to feed our search. So our intent model will have realized, this is a product request, but now we want to understand what kind of product the user is actually looking for. So we need to find out, or yeah, we need to identify the entities. So one entity would be the suit here, the category. Another one would be the color black, and also the maximum price here of $200. So that's the goal here for our named entity recognition task. Just up front, also the training data format for our named entity recognizer is a bit more complex than for an intent model. So when we train the named entity recognizer, we basically have a very similar format as a label. So we give it a sentence, an expression in our training set, and our labels will basically be those. We will tell them, hey, at each character here, this entity starts, there it ends, and by the way, it has this value. So the label structure is a bit more complex here. So yeah, this is... Yeah, so the goal, as I just mentioned, is to identify all fashion-relevant entities in a user product request. And we trained a conditional random field to extract the entities. And yeah, I mean, a conditional random field is way more complex than explaining a support vector machine and a recurrent neural network. So I'm gonna try to motivate it with a hidden Markov model, which is very similar to a conditional random field. But the idea is that, look at this acyclical directed graph. You have some sort of states here from 1 to 5, and you have some sort of symbols here. And the idea is that those states here from 1 to 5, you don't observe them, they're hidden. And you try to infer from those features here, those symbols, you try to infer what these states are. So in the end, after this whole thing is trained, for example, you could see like a sequence of symbols, and you would like to know, okay, which states were actually, which sequence of states was actually involved in generating this sequence of symbols. In our world, this sequence of states are the entities, and these symbols are the features or words. I'm going to talk about this in a second. And this sequence of symbols is a sentence. So basically the thing is, in order to, for example, to find out about the sequence of states or entities for this sequence of symbols, there are many different sort of sequences of states that actually are possible. So one would be, okay, the first symbol is this strange thing here. So it could either have come from state 3, 4, or 5, because no other state actually directs to this symbol. So we know there are 3 options already, and they have to start with 3, 4, or 5. The second one, the star, it would be like, okay, we started at 4, we got this strange symbol, and then where can it actually transition to the state? So the red arrows, they are basically the transition probabilities. And for example, the probability to transition from state 4 to 3 is very high. But 3 doesn't connect with a star. Oh no, it does. 3 connects with a star, but only very lightly, so probability is very low. So we could take the sequence 4, 3 already to produce these 2 symbols here. And then you can go on, and you come up with numerous sequences, and then you can use like this, I think it's called Viterbi algorithm, to find the sequence that is most likely. Yes, so you end up training this whole system. And yeah, I mean, in our entity world, it's basically you have these transitions from one entity to another that is also intuitively understandable. For example, quite often a color is followed by a category, because in a lot of requests we have like, I'm looking for black shoes, or I need a red dress, or white, I don't know, jeans, or something like that. So generally, if this state here would be, for example, the category entity, then it's quite likely that this would be, for example, the color entity, because the transition probability from color to category is quite high. Yeah, so as I mentioned here, we don't use the words directly, we use features. And features are generated by just bunching, or like putting together a bunch of attributes of a word. And it could be, is it lowercase, is it uppercase, is it a title, what's the preceding word, what's the following word, all these kind of features we bunch together. And we use this to predict the probability that, given all these features, what's the probability of it being entity X or whatever. And then the conditional random field also takes into account the transition probability, and then it finds the most likely sequence, and that's what's the output of our model here. So after we train this, we see, for example, very likely transitions, and we have something which is which is very intuitive, that usually brands have more than, or not usually, but quite often brands are multi-word entities. So they basically consist of 2 words. So an example would be, what's the Hugo Boss. Hugo Boss would be a 2-word brand, which here it shows that the beginning of a brand is very likely to be followed by the end of a brand, which L is here for last. And the same is for a product name. Usually we have product names are 2 words, so the beginning is followed by the last product name. But then, yeah, after all these BL relationships, we also have like relationships like I just mentioned, so from color to category and things like that. And you can see that the algorithm actually learns these transition probabilities quite well. Yeah, so in general, the conditional random field is very fast to train and very fast to evaluate. It helps to generate synthetic data for the algorithm. So we did exercises like just generating new expressions with, for example, mistakes in the brand names, and putting the brand names in different positions and all these kind of things. So that greatly helped the performance of this named entity recognizer. And in general, picking the features is more like I mean, there's some intuition behind it, but it's also a lot of trial and errors, and the performance is very sensitive towards the number and types of features that you use for this conditional random field to train it. Yes, in general, we have like for these major entities that we kind of focus on, so category, color is an important entity. We really want to make sure that we get those right, so that we have like some sort of sensible search results. We have sort of recall rates in the 90% area. So we're quite happy with that. Yeah, and that's it. So please let us know if you have any questions or so. Thank you. Because it doesn't work any better. It's very simple. I think the main reason is that given the high dimensionality of the word embeddings that we used, so we used 300 dimensional word embeddings, which are quite sparse. Usually linear kernels work quite well, so there was no need, at least from. Yeah.
So yeah, as I said before, we started as a human-backed service. So we had quite some expressions, and we then just labeled them. Yeah. So yeah, the data, data labeling, data preparation, all the data things. It's quite a lot of work, and you need like proper data to train those nets. Also with the image, we labeled, I don't know, I think 100,000 pictures. So quite some tasks. We also built an app for that. So if anybody has those tasks, speak to us. We're happy to share it. Yeah, but we had those. I mean, we are only applying things in our searches when we have those requests. So, if a new intent or also new entities come up regularly by users because users ask those questions or write those things, we then implement it. So we don't. In the beginning, we started and having like quite even more intents and also entities. And then we realized, okay, it's too much. It's better to go step by step. And from your real data, see what people actually, what users want and what they need, what they're looking for, and then implement it. And yeah, that worked quite well. Oh, zwei hintereinander.
So for our language understanding task, not really. I mean, I don't think it's very common yet to use pre-trained models for these tasks. It's very common for computer vision. So for our data enrichment neural networks, we used pre-trained models and just fine-tuned them. But we didn't use it for our natural language understanding tasks. And to be honest, yeah, I mean, for support vector machines, I wouldn't know of any sort of pre-trained models that I could use. And the same actually for conditional random fields. So there's nothing we really considered or tried, but we definitely did for our computer vision tasks.
Yeah.
Yeah, that's quite good. It's probably heavily a bit biased, the data set, towards product requests. So, but no, it generally works really, really well. I mean, one thing I forgot to mention is that, for example, for the word embeddings, for example, we use pre-trained word embeddings, so we don't train the word embeddings ourselves. So, I mean, but this is usually not considered, hey, I'm using a pre-trained model. I'm using basically a numeric representation of a word. In this case, we're using Spacey's open source library to get the English word embeddings. So if you have like a language, Greek or whatever, unless Spacey doesn't have word embeddings for it, or you get some word embeddings or train some word embeddings yourself, you couldn't use or you couldn't train our SVM model or yeah, you can. I mean, it's nothing special about our SVM model. You could train just an arbitrary linear SVM model.
Okay, thank you all. Have a nice day.
Thanks.